Okay, so hello, welcome everyone. My name is Marius. I work at SprintEins. This is about the optimization of CI/CD pipelines. Even though maybe 99% here are German and I am too, I'll do it in English anyway. Practice session, so to speak. I'll try to minimize the usage of Dinglish, whatever. Brief disclaimer about our company, or about an introduction about our company. I work at SprintEins, which is a medium-sized service provider. We are now 10 years old. We have mostly our offices in Stuttgart and Bonn and just a few other smaller offices. We work in all kinds of sectors, mostly automotive and logistics and banking. And well, we create software with a focus on making it actually usable and not like some pieces of software that many of us also know in daily life. And we cover the entire life cycle, including, of course, cloud engineering and operations, which is why we are essentially here. And I want to avoid talking at you the whole time. I want this to be a little bit interactive. So this means if you have an understanding question, raise your hand right away and ask me. If you think what you have in mind is more of a discussion, then please move it towards the end. And I will also engage with you from time to time. So let's practice this by making quick polls. So no sleepy. Please raise your hand, all of you who write YAML stuff, who actually build these pipelines, not just use them. Okay, so we have 99. I think everyone, pretty much. That's good. That means that you are right in this place. Just briefly about me, I have a software engineering background, more than 10 years, worked in a research institution for most of my time. I also have, of course, spare hobbies, see the icons. But professionally, I worked with CI/CD platforms for the last 3 years, like GitLab, GitHub Actions, Azure DevOps, and of course, cloud tech, like Kubernetes and all that stuff. And what I learned in the area of CI/CD is that CI/CD is super great, but if your pipelines become too slow, it kills your developer productivity. And they start calling you and be annoyed by this. And most of you will probably know this meme. And it applies to when can you slack off when the compiler is running. Yeah, okay, but now you can replace the compiler with your pipeline and it's the same thing. The compiler runs in the pipeline anyway. And it's even slower than just the compiler in the past. So another interaction with you guys. Do you not have any idea how long your pipeline runs? Option 1. Who has no idea? Okay, since everybody is here to learn something how to make it faster, you probably already have some slowish pipeline. But anyway, some here that complete in less than 10 minutes. Oh, that's almost half.
Average or?
Yeah, let's say the fastest one. Okay, so who can take a big a nap or a coffee break, 10 to 30? Ah, that's also still a quarter. And who goes to lunch every time you run a pipeline? A few still, yeah. That's a great offers great potential. So for the structure of this talk, I want to begin by discussing a few frequent causes that I saw for slow pipelines. I will at the end conclude, but the majority of the talk will be about the 5 different tips that I want to give you. So let's begin with the frequent causes for slow pipelines. I have tried to cluster this in 3 areas. Area number 1, your agent infrastructure. You build agents that pick the job and run them. They are somehow not appropriate. For instance, because you have what a German calls a Möhre, a slow runner that is not appropriately equipped with memory, CPU, whatever. Maybe another example could be you have a static fleet of build agents, but it's a small number of build agents and your jobs queue up because you have too many at some points of time. Or maybe you have some kind of dynamically, elastically scaling runners, but always spinning these up, these VMs, is costing you a lot of time. Number 2 would be that the jobs that you have inside your pipeline are not well optimized. For instance, could be left out and run in some other place rather than running it all the time, or they are not tuned properly, like using caching. But we will get into these tuning tips in a second. And number 3, when you consider your pipeline to be like a graph, then maybe the graph structure is bad. Maybe the sequencing, the granularity of the jobs is not appropriately done. So for instance, you have maybe a fat job that does a lot of stuff after another that could have been broken down into smaller ones. Or maybe you have your jobs wait on other jobs for way too long. For instance, using the stages concept that some CI/CD platforms have, like GitLab. Or maybe because you use some kind of lock where you make sure only one job runs at a time. For instance, with GitLab, that's the resource group thing. GitHub Actions has concurrency, and this makes also jobs wait longer. This is a hard question, so it's fine if you raise your hand right away. Who doesn't know which of the causes apply to you? Only 1 or 2 people. Who thinks it's at least, you can raise your hand multiple times, the build agents are too slow? Okay, like 6 already. Who thinks the jobs are not optimized? Maybe caching can make them faster. It's already 12, 13. And who thinks it's the structure of my pipeline? Well, 3. So some hands go up very quickly. Good. So let's go to the majority, the major part of this talk, the 5 different tips. This is an overview. I won't read this out now because we go into each point now anyway. Just to know for you, I tried to make the tips generic. So they don't just apply to a specific CI/CD pipeline, but hopefully to any. Good. Number 1, we need to get a picture, an idea of where to begin. We need to make an analysis. Because just before I gave you 3 common causes, but which of these 3 apply to you? This is a highly specific field. Everyone uses a different CI/CD pipeline platform. Everyone has very different tools running in these pipelines. So what gives? You need to begin analyzing. There are 2 kinds of ways you could do this. Either the platform offers something for you, including a nice clicky web interface, for instance, Azure DevOps or GitLab. Some popular platforms somehow forgot to include this feature. I'm a bit baffled why, but this can happen. And still, even if your platform doesn't have it, it doesn't matter. All the platforms I looked at least they expose this, let's say, metrics in some shape or form via some API. So then you can think about choosing some other tooling that you know from the observability area anyway and use those to scrape these data out and then visualize it. This could be Prometheus and Grafana, and for GitHub Actions, you could use an Actions exporter, just as an example, but you always have to research the concrete solution for your concrete stack yourself, but this is usually an easy thing to do. There's also, just so that you know, if you already use software as a service observability things like Datadog or something else, they often have plugins, so they also support CI/CD. Maybe you just didn't know. And there are even dedicated CI/CD observability solutions that only do that, like Trunk CI Analytics. Just 1 or 2 screenshots what the integrated tools or third-party tools could look like. So we have a pipeline here that runs a little bit too slow, admittedly, but I can see a breakdown basically of my slowest steps, and I know then, okay, this is where I might want to start. Another one for GitLab, the top right, is the integrated GitLab feature, the pipeline success and duration chart, which shows me the last 30 commits. I don't know how this is useful, but someone at GitLab decided that 30 commits are enough. I would say 300 commits are maybe enough, but it depends on your teams, and that's team sizes. But you can still scrape this data and visualize it with any other system that has any retention period you want and want to pay for. And also one nice thing that so far I have only found in GitLab is that when you want to look at your job dependency structure, you need to, at best, a way to visualize it. Because otherwise, I have a 400, 1000 line of YAML files with jobs that somehow depend on each other, and it becomes difficult to understand when a job waits on another one. And in this image, I clearly see this job waits on that one waits on that one waits on that one. Okay, I can work with this visually. I understand it immediately. So now that, let's say you have done the exercise of looking, checking out what is slow. Let's say we had finished the talk, so you know the other 4 tips, and now you have this problem of, okay, where do I start? There's no easy solution to this either, because what you essentially want is a good cost-benefit ratio. You want to put some costs in, the time you spent on optimizing, and you want a great benefit out of it because the pipeline is now faster and your developers profit from it. And at the beginning, it's quite difficult to estimate. Let's say I have this 10-minute job and I have an idea of 3 techniques to apply to make it faster. How much will it make it faster? 2 times? 0.5 times? Will I make it slower accidentally? You can never know. This is something you have to trial and error because every system is different, and don't believe other people's benchmarks. You have to do it for your own system. Even the same tip in the same platform may apply differently if one uses the managed agents of I don't know, github.com, and the other ones use their self-hosted ones, and suddenly everything behaves completely differently. But let's look at concrete other things. Choosing the right agents. In my mind, I think you have 2 very important decisions to make here. Decision number 1 is, do you want to just pay someone to manage all the build agent infrastructure for you? So that's the SaaS model. Or do you want to do this yourself in some way? And the other one is, irrespective of the first one, do you want a static sized pool of agents, or do you want an elastically scaling dynamic pool of agents? And if I combine these 2, I get a table with just examples. Like a set of VMs would be static, self-hosted. Using Kubernetes and installing the agents inside would be dynamically scaling, but still self-hosted. And with SaaS, most of you probably have already used something like this, the managed GitLab.com runners, GitHub.com runners or agents. But there are even niche products where you can pay someone to manage a fixed set of fleets of agents for you. That also exists, like a Netzfabric offering. But this is really, you have to Google this quite a while, for quite some time to find something. And now we have these different decisions. What do we do? Well, we make a list of pros and cons. And as always, if you have some pro on one side, you can negate it, and this would be the con on the other side, respectively. So let's look at these things. So if I have a static pool, my fees are predictable. I know how many servers I rent. I know how much a server costs. Multiplication, done. But predictability is not the same thing as being really the lowest possible costs. It could still happen that your dynamic fleet is even less costly because you have elastic scaling, and this can even be including scale to 0. So during the night, for instance, when nobody is pushing code, your pipelines can go to sleep, and the runners that run them. But let's look at other examples. So we have a static fleet, and assuming that you don't have queuing problems of jobs stacking up, a static fleet can often run your pipeline faster. Why? Because you have better caching locality, because these agents are long running and therefore can use the local disk cache for a long period of time. You have to still take care of sometimes cache cleaning so that your disk don't fill up, but it's still a good way to go. And you don't need to wait for the VM to be there because it's there all the time anyway. There is no VM provisioning time. But of course, it also has cons. The static pool, like we do not have elastic scaling, which we do get with the dynamic fleet, which is great if you sometimes have many pipelines at once, and sometimes you don't, because you have, for whatever reason, a different output of your teams at times. And I also found that dynamic fleets often have less maintenance because you no longer have to take care of individual VMs and all the scripting, but you have some managed platform underneath, which takes already quite a bit of burden. But I'll also get into this in a second a little bit. So we still say in the static dynamic decision, let's say you wanted to make it yourself and you want to create a static pool of agents, then I would highly recommend against making this all by hand, maybe at the very beginning when you're still experimenting, but later on switch to IAC. Make it infrastructure as code, Terraform, Ansible, any other thing. It doesn't matter. And while this makes you slow initially, because you need to create all the scripting and test it, it helps you in the long run, because you need less and less maintenance effort to keep these things afloat. And if you wanted to, you could even have some kind of manual scaling. What I just mean is maybe in the morning you update in a scheduled pipeline your Terraform variable to number of runners equals 6, apply, and then in the evening at 6 you set it to 0 or whatever. So you can even build your own crude auto-scaling this way if you wanted to. It's no longer really static anymore, but just making the point, infrastructure as code is a good idea here. And with the dynamic approach, what I just said before, don't do it all by yourself, use a managed platform. Typically, this means Kubernetes, but you may have other platforms to look at. If you use something like Kubernetes, of course, use the managed ones, unless you are in the field of liking to run your own Kubernetes. And then many platforms have compatible things to just install into Kubernetes. So for instance, with GitLab or GitHub Actions, you can just install software that is either official or semi-officially supported by the respective platform, and you have a auto-scaling fleet of agents. Anyone here using Azure DevOps? Yeah, a few. Here the options are, it's more dire, this field. Either you can use the completely managed runners, then you're fine, but if you cannot, then you can either use the scale sets. They are automatically scaling VMs, but they run one agent on one VM, so it's not really resource friendly. There's a Terraform module also. It's running more resource friendly as a container, but it doesn't have auto scaling, so it's static. Microsoft is working. They told us, how do we say, unter der Hand? They told us, yeah, we are working on something in public preview at some point at the end of year. I'm not getting excited to wait for this to happen. And what our custom actually built, which I wanted to present, but it's way too complicated. If you want to know details, ask me afterwards. You can use Kida, the Kubernetes event-driven auto-scaling. They have a plugin to scrape the number of pending jobs of Azure DevOps and then modify a HPA to then scale your agents. So this is a solution that can work. And now I'd like to check how are you guys doing it? So is anybody here using certain number of VMs and you run your agents on them? Okay, 4 people, 5, 6 people. Who uses dynamically scaling? Number 2, something like Kubernetes. Also 3 or 4 people. Who uses something like software as a service but static fleet of agents? No one, that's what I expected. And who can sigh and just pay someone to do it? Yeah, that's a third. Well, also 6 people, 7 people. So yeah, you're lucky. Okay. Are there any understanding questions so far? No? Okay, so caching. I couldn't resist them using some Photoshop to change the picture. Let's take a quick step back. What is caching? Why do you cache? I think everybody knows, but just to put it in my own words, you have some work that takes a lot of time, typically compute intensive, and this needs to be done at several points. So you don't want to repeat it, so you do it once, store the result, and reuse the stored result, because you have already done it anyway. But what can I cache? And I have 3 examples for what we could cache. Number 1, you are typically using dependency managers of some shape or form. apt, npm, pip, I don't know. Many of these actually have a cache themselves, some internal cache. So what essentially happens if you run npm install, the npm install downloads it to its own cache and copies it also to the final destination like the node modules folder. Why? Because if you run npm install again and somebody has deleted the node modules folder, all npm needs to do is some metadata information, no longer downloading anything, just copying it from the cache folder, from the disk, to another folder on the disk, which is of course much faster. The number two would be that you could of course also cache the dependencies themselves once they have reached their final destination, like the node modules folder. Or number three, there are often some kind of intermediate artifacts. Very often a typical example, build artifacts, like a C++ object file. But even other languages, like dynamic languages, have this. So for instance, Webpack uses a .cache folder that you might know or maybe might not know. And when it comes to caching, we can go about this in two different ways, or maybe in even more different ways. But these are the two that I show you. The one is use the CI/CD platform caching. I will explain it in a second. And another option that I also picked up recently is to use Docker build cache, Docker build cache, something like buildkit, and you move things that used to be in your pipeline in the bash script section, and you move it into a Docker file, and then instead run Docker build, even if you do not want a Docker image, even if you don't care about the Docker image. But ideally, you want a Docker image anyway, and so everything threads together, but it depends on the use case. So let's look at the examples. So, platform caching. This is an example what I mean. You have a job definition. In this example, it's a GitLab CI/CD. And what you add is a piece of YAML segment, and this defines a cache. And caching happens in two different ways. Most typically, it's the distributed way. The basic idea is the cache is stored remote. The agents download the cache if available, extract it. Then the job runs. I don't know, my bundle install command, for instance, runs. And then finally, I'm zipping everything up and sending it back to the remote storage. Of course, this takes time. Downloading, zipping, uploading, unzipping, all that, right? Sometimes some platforms have local caching only, like GitLab by default, self-hosted runners. Here, the cache is stored locally. Of course, this means you get cache misses if one job is run on agent number A, and then the second job runs on agent number B, and the cache is only available on agent A, and then you would get this problem, but not with the distributed caching because it's uploaded to the server and then the other agent can download it. So it's purely for the agent scaling why you do this distributedly. Some tips before I get over to the Docker approach. Try to have not one huge cache that contains everything, but have several caches, smaller ones, that you up and download only in those jobs where you need them. So for instance, you could say you have a dependency manager cache, a dependency cache, maybe a test cache, whatever different things in your case make sense. In case you use GitLab, there are some tweaks that I have not seen in other platforms. For instance, you can control, do I always want to download the cache and upload it at the end? Or maybe sometimes I just need to download it. Could be a scenario like a testing job that only needs to download the cached dependencies and not upload them again because it's not the test job does not have a business of warming the cache of the dependencies. It just wants to use them if it's there. And also a very easy tip, fast feature flag, use fast zip to cut down your zipping time in half. I tried to ask the GitLab folks why they don't enable this because this is a feature flag that exists since I can remember and is off by default, and I've never seen a problem with it. Okay. We have a very simple case. We have a node modules application, a node application, and you have a cache warming job that just warms the cache. You have a testing job, you have a build job. Note how these two latter jobs always also run yarn install. And why is this? Because caching is not reliable in the CI/CD platforms. Maybe it was never uploaded, you cannot rely on it. It typically works, but you should be sure. And if we translate this to Docker, the basic idea is that you write a Docker file that contains multiple stages. I hope that you are maybe familiar with this. Essentially, what you can do with this is tell the docker build command to only run specific sections of the Docker file, or let's say up to including a specific section. So the yarn install would be moved into the first layer, where all we do is copy in the code, run yarn install, that's it. The second layer would be just running yarn test. The third layer would be just running yarn build. And then our pipeline YAML, the yarn install stuff disappears, and instead you run docker build, docker push. And this cache that you made is essentially published as an image. And since image publishing is typically reliable, you also have a reliable caching mechanism. And you get a bunch of examples. So for instance, let's look at the second one first, the skip running commands that were already cached. What I get, the problem is with CI/CD platform caching, yarn test is always executed, yarn build is always executed, and it always takes whatever time it needs. With Docker, this is no longer the case if the stuff that happened here was already cached. Example, somebody changes the README file. Then here, this would still mean the whole pipeline runs. You always take time to build and test it. With Docker, assuming, of course, the README is excluded from the context, it just, the whole pipeline takes a few seconds because all the jobs just see, oh, everything's cached. And another example is, another advantage of Docker is that tools like BuildKit, they combine caching locally and remotely. That means if you have a machine that runs a certain building daemon, like a BuildKit daemon for a long time, so it can put stuff into its local disk as well, it will always get a new job and it will first consult its local cache if it already has caching information. Only if it doesn't, it also takes the remote cache and downloads it. And this download is additive. So the local cache keeps growing and therefore you get less cache misses. At the expense, of course, that you need to make sure of cleaning, but something like BuildKit already has garbage collection integrated. But there are also disadvantages. So for instance, let's say your job, the testing job, produces artifacts that you want to upload to your CI/CD platform. Let's say an XML JUnit report drops out of your yarn test, and then you want to put it somewhere to visualize and whatever. You have to scrape the stuff out of the Docker container because it's no longer on the normal native file system of the agent. You have to instead create a container of that image that you just built, then run docker copy to get the file out, and then destroy the container again. That's a little bit wonky, but you can make a simple shell script that does this for you. And also, the console log output is a little bit polluted because, as you can see, there are always new lines being spat out by BuildKit, like this done and all this checksum stuff, and it makes it a little bit more difficult to read. However, you should also be aware that there are tools that use Docker under the hood that solve this kind of problem and make nicer output and add some more fanciness to it. I don't have deep experience with it except for Earthly, which I used and liked, but there are a couple of tools you can check out. And as I said before, there's a demo project which I made with GitLab where I think the job logs are still there. You can even still see the 4 executions and compare the runtimes and see what the benefit is. But these are my benchmarks, so they do not apply to you in general. It's always, unfortunately, a trial and error exercise. Before, as a final word about caching, there's always a big pitfall, which is that caching suddenly made things worse. So essentially, you always need to measure how much things have really improved. Measure it before, measure it afterwards. And there are some things that can go wrong. So for instance, there's always cache misses. Cache miss, cache miss, cache miss. This is also called cache trashing. So there's no benefit because you just lose time uploading and downloading and zipping, but you never get anything out of it. Another problem is that you might have incorrectly configured the caching. So for instance, you configured an incorrect path, and then you think that caching has worked because there's no error message, but it actually hasn't. So for instance, I don't know, Webpack expects the cache to be in some folder, and then this folder that you think is being used, you put it into your GitLab CI/CD caching so that it's uploaded and downloaded, and it turns out it doesn't even work, and GitLab is sometimes weird and it prints, yeah, I have done everything with the caching, it works. And then if you look at the files, it's nothing there. So the success messages may be deceptively lying to you. So this is something you find out later. And of course, finally, as I said before, downloading, uploading, it all takes time. And especially it takes time if the connectivity between your agent and the place where you store your stuff is not good. If they are not somehow close together, go all the way over the internet. Yeah. Or if you have two large caches, which you always up and download, if you have defined them like this instead of defining smaller ones, then this also hurts your overall performance. Okay. Does anyone here not use caching or don't know if you use caching? Nobody raises their hand, maybe one. Who uses the normal CI/CD platform provided caching? That's half the room, I would say. And who here uses maybe also or exclusively Docker caching? Two, let's say two. Okay, great. So for tip number 4, the dependency graph. I look at this from 3 different angles. So the first angle would be breaking up big jobs. I essentially said this before, just to reiterate. Sometimes you have jobs which take a very long time, and all these steps that are run after another may be not related at all. So for instance, you have a job where you already set up the C++ compiler, so let's compile application number 1 and application number 2 because we already have the compiler set up, great. Yeah, but they are 2 completely unrelated applications. You could have split this up into 2 jobs. Even if splitting up means some extra costs because you need to set up the compiler twice, you need to measure how much is this costing you and is it maybe still better to run it in parallel. Number 2, let's think about it. What is the greatest optimization of all time? They do not run something at all. And just as a few examples, when things are run that shouldn't have been, I said this before, you have a README that you changed, but then you build your entire thing again. Or maybe somebody has changed only front-end code, but you still do back-end building and testing and whatever. Or you are running maybe very long-lasting jobs. This could be anything. This could be your integration tests, maybe expensive end-to-end tests, whatever. What can you do? Well, for the last example I just said, you move the stuff out. You move it, for instance, to a scheduled pipeline that runs regularly and maybe also on very specific conditions. Maybe a release requires you and running an end-to-end test, but not every push to a feature branch requires you to run end-to-end tests. And all the platforms have some kind of mechanism to put conditions on when to run these jobs. With GitHub Actions, this is the if. Then with GitLab, I think it's when, and with Azure DevOps, it's condition, I think. So everybody knows best how to call this stuff. So you get different YAML syntax everywhere. That's great. But the basic idea is the same. You exclude, you make sure that jobs only run in specific cases. Okay, and the third tip of 3 is the dependency tuning. I have an example here. This is a GitLab screenshot. There's some Python application, and we first lint it, then we test it, then we build and push the Docker image. And semantically speaking, it makes sense to do this after another. I would say it doesn't even lint, let's save the work from, let's not do the rest. And semantically, I agree. But technically, I could have run the 2 or even all the 3 together. Because the first job that fails then also cancels the other jobs. And I save time this way. Okay, for the last tip, optimizing the jobs themselves. Are there any questions so far? Understanding questions? Okay. So sometimes you have jobs which are just plainly slow, and you think this is normal. You are compiling a big application. Of course it takes long. You're running end-to-end tests. Of course it takes long. Yeah, it's a no-brainer. You've never seen it before in any other way before. But what's still weird, but it works, just Google or whatever for speed up and then a job description of whatever's happening. And you will be surprised that sometimes you can speed up things that you didn't think are possible to speed up. The general idea of what these tips that come, what the search engine spits out, is typically either along the lines of caching, which we just talked about before, or parallelization. So going into a concrete example or examples with caching, what I learned over time is that many of these tools that you invoke in your pipeline, they have some kind of internal cache that you might not even have known about. But once you know about them, you can, of course, scrape this cache folder out and upload it to your platform and then reuse it in other instances. Doesn't matter if you use CI platform caching or Docker caching in this example. So for instance, with Angular, since version 13, they have explicit caching tips, caching configuration options inside. And before that, that was even also possible, but you had to know the secret location of the cache, and now you can specify it, and it's a little bit nicer. And I'm not against it if my compile time suddenly gets in half, right, of my Angular build. And Angular is not fast to build anyway. And the other idea is parallelization. Similarly here, what you may not know is the tool that you call might support some way of divide and conquer strategy, where the tool somehow splits the work up into many smaller jobs, does each job in parallel, and then merges the result at the end. So one example would be variant number 1, that this happens in a single build agent. Think of something like the make of a C++ application with the J4, and then you run 4 cores compilation in parallel. But also tools like Python, and when you run PyTest, there's an xdist plugin to parallelize the tests on the same machine. Since this happens on the same machine, be cautious if it's limited in resources. This won't be helping you, because if you only assign one virtual CPU and then you run compilation with 10 CPUs, how does this work? I mean, you just get throttling and memory problems maybe. For this, there's another variant where you split it across build agents. So some tools allow you to define, hey, call me Python, run some tests, but only run a third of the tests. And this way you split it into different CI/CD jobs, which then completely run in parallel. And then these plugins still have a ways of merging the result. And here also, of course, everyone can Google like you want it, but I found that split something into multiple platform name jobs got me sometimes quite good results. Okay, to conclude. First of all, my advice would be don't fall into the premature optimization trap. Write your pipelines normally. They will grow, of course, like technical debt, everything grows and becomes slower and more annoying, and then you start chopping. I fell into the trap of saying, oh, I make premature, I already know what I'm doing, I'm the expert, I'll start writing optimized pipelines. Yeah, I didn't have this such great experiences. Also because people start no longer understanding things, but I will get to this in a second. Then what I said before, measure always, and what I mean, measure yourself. Don't rely on other people's benchmarks. What you can, of course, do is chances are high that within your own company, maybe you use the same CI/CD platform, maybe you use a similar tech stack. So optimizations you make maybe in one project might carry over to another project. So if you document that with Azure DevOps and this kind of agent, optimizing an Angular build can be done like this, and you typically get a performance speed up of factor 2, write these things down for your own internal community. It'll be still worthwhile. And finally, about costs and maintainability of optimized pipelines. In essence, there is no free lunch. Sure, sometimes you can really cut away work, so you can reduce the work. But typically, let's say that the laws from physics, you have a fixed amount of work and it's produced by power times time or power over time. And you want to reduce time because you want pipelines to be faster. Of course, then you need to increase the power again. And this means spending more money and having more agents or faster agents or whatever. And it's a really quick fix. Like the easiest fix, spend more money, buy a better machine, no engineering hours spent, right? But let's see how much the bill then is. And finally, also, if you write pipelines and you make them more and more optimized, then you get very long, very complicated statements, and sometimes this makes it harder for your peers to understand. There's no panacea to this. It's unfortunately the way it is, but still I believe that this is a worthwhile exercise because your colleagues, your developer peers will thank you if your pipeline has become faster. I've already put a bunch of links on the other slides when it was applicable. There are a few more ideas from my blog and from other people's blog, what to look at for concrete optimizations. And I conclude and open the discussion if you want. So maybe a question. Who here has already had the endeavors of optimizing, and how did it go? Yeah, please.
Yeah. One thing I optimized was a link check of our wiki, where we check all the external links if they're still available, and the naive approach was to scan everything one at a time, and took about 1 hour to do my job for the wiki. And then I implemented it in asynchronous way, and now it takes most of the time about 2 minutes.
Yeah.
Check the whole wiki.
Yeah. Yeah. Any other optimization approaches? Or what? Yeah.
Question.
Sure.
If you measure your runtimes of jobs, and you have executors or nodes or whatever spinning up, and they serve different jobs. So you have, for example, a node accepts 2 jobs simultaneously, 2 very different jobs. And so what I noticed sometimes is if one job runs on a machine that has where nothing else is running, it runs much faster, because sometimes it so you have variations in your measurements.
Yeah.
How do you handle that?
I handle this by also instrumenting the agents and correlating the results. Of course, this means I look at a very concrete, like let's say I see a very long running pipeline that is typically faster, then I look at this specific instance that ran for a long time, and then correlate these with the metrics from the agent that ran the job. And this way I see, is this machine suddenly busy with other stuff? I mean, it could also be that it's currently running APT upgrade, or I don't know, whatever happens, and this already takes...
Correlated with the CPU usage or base
Yes.
bits.
Yeah.
Thank you.